This morning, you made a choice. Maybe you got up. Maybe you negotiated with the snooze button like it owed you money. But here's the question that sounds like sci-fi and yet is legal physics to ask. What if every choice you didn't pick still happened? Not somewhere like Canada, somewhere like a different branch of reality. Now, before anyone starts selling multiverse travel packages, let's be strict. Parallel universes are not confirmed facts. They are hypotheses, serious ones, living at the edge where mathematics outruns observation. Tonight, we're going deep. But we're going with a rope and a flashlight. We'll meet three multiverse suspects. 1. Quantum branching, many worlds. 2. Cosmic bubbles, eternal inflation. 3. String landscape, many possible settings for physics. And we'll end with the only question that matters. How would you ever test this without turning the universe into a lab rat? By the end, you'll understand why parallel universe vibes show up in real physics, what each multiverse idea actually claims, what evidence would look like, why many scientists remain unconvinced. And yes, there will be humor. Because if reality is branching, there is definitely a version of me who tries to explain quantum mechanics using jollof rice and regret. All right, let's open door number 1. Quantum mechanics is the most accurate theory humans have ever used to predict nature. It's not pretty accurate. It's your GPS, your MRI, your smartphone chips accurate. But it carries a scandal in its pocket. In quantum theory, objects don't always have a single definite state. They can be in superpositions, like a coin spinning, but deeper. Not heads or tails, not even unknown, both in the math. Then we measure and we get one outcome. So the universe has to answer a rude question. When does maybe become is? Some interpretations say the wave function collapses. Others say no collapse, just evolution. And that's where Hugh Everett III walks on stage in 1957 with a paper and basically says, what if the wave function never collapses, and the appearance of collapse is just us? This family of ideas is often called the Everett interpretation. The popular nickname is many worlds. And a small important detail, many worlds is the label people use. Everett's original framing is often described as a relative state formulation. Now here's the vibe. In many worlds, the universe doesn't pick one outcome. It keeps all outcomes, each in a different branch that no longer interacts. So when you measure a quantum event, you don't force reality to decide. You discover which branch you're now in. So yes, there's allegedly a branch where you went to the gym, and another branch where you bought gym clothes and used them to become a motivational couch philosopher. Both are consistent with the equations. Now, the obvious objection, if branches exist, why don't we see them? Where are the other worlds? Are they behind the fridge? This is where decoherence enters, like a bouncer at a nightclub. Decoherence is the process where a quantum system becomes entangled with its environment. Air molecules, photons, vibrations, so the delicate phase relationships that allow interference get effectively washed out. Think of it like this. A quantum superposition is like two melodies that can interfere, harmonies and cancellations. Decoherence is like the universe turning on 1,000 loud fans until you can't hear the interference pattern anymore. The result? Things start behaving classically. Not because quantum rules stopped, but because the environment records information in a way that makes certain states stable. So, many world supporters often say decoherence explains why branches stop interfering. That's why each branch looks like one consistent reality. But here's the subtlety. Decoherence doesn't, by itself, tell you which interpretation is true. It explains the appearance of classical outcomes, but it doesn't magically stamp one world only on your forehead. Decoherence is basically reality saying, I'm not collapsing, I'm just unfollowing the other outcomes. Now comes the big headache.
Quantum mechanics predicts probabilities using the Born rule, those famous squared amplitudes. You run an experiment many times, outcomes appear with certain frequencies. But in many worlds, all outcomes happen. So what does probability even mean? This isn't a silly philosophical complaint, it's the central technical pressure point. There are proposed derivations, decision theory arguments associated with Deutsch and Wallace, symmetry arguments, and more. But there's active debate over whether these derivations avoid hidden assumptions. Many worlds is elegant, but the why these probabilities question is where even friendly critics lean forward and say, okay, show me the accounting. Because if reality is branching, I want to know who's in charge of the spreadsheet and why my branch keeps getting the unexpected expenses tab. Now, here's where the internet gets messy. Parallel universe can mean different things depending on which physics problem you're trying to solve. So let's organize this cleanly. A famous organizer of these ideas is Max Tegmark, who described multiple levels of multiverse possibilities. But we'll keep it simple. 3 doors. Door 1, quantum branches, many worlds. Interpretation level multiverse. Same laws, but outcomes branch via unitary quantum evolution. Okay? Door 2, inflationary bubbles, eternal inflation. Inflation is the idea that the early universe underwent rapid expansion. It helps explain features like large-scale uniformity and near flatness. And observations of the cosmic microwave background are consistent with inflationary expectations, while also strongly constraining inflation models. But some versions, eternal inflation, suggest inflation never ends everywhere. Instead, it ends locally, producing bubble universes like ours inside a larger inflating background. So where's the evidence? People have searched for possible signatures of bubble collisions imprinted in the cosmic microwave background. Do we have a confirmed detection? Not in a way the field agrees on as definitive. What we have is ongoing constraint setting, methodology, and theoretical work on what a signal would look like. Cosmologists are basically staring at the oldest baby picture of the universe and asking, is that a bubble collision scar, or did the universe just smudge the lens? All right, door number 3. Door number 3, string landscape. Many settings for physics. String theory, in many approaches, allows a huge number of possible vacuum solutions, often discussed as a landscape, which could correspond to different low-energy physics. This is one motivation for multiverse talk in high-energy theory. But the landscape idea is controversial because if there are many possible consistent settings, it can be difficult to extract unique testable predictions. In other words, if the theory gives you a menu with a million options, how do you prove the universe ordered this one? Now, let's be fair. Here are the strongest skeptical objections, presented cleanly. 1. Testability. If other universes can't interact with us, how do we test them? This criticism hits hardest against multiverse versions that lack observational hooks. 2. The measure problem in cosmology. If there are infinitely many bubbles or regions, how do you define probabilities over them without ambiguity? This is a serious technical issue, not a vibe. 3. Probability foundations in many worlds. Even many worlds advocates agree the Born rule and probability interpretation require careful treatment. So skeptics say, don't confuse mathematical possibility with empirical reality. And supporters reply, don't confuse hard to test with not science. Some things become testable later. This is a live frontier. And it is. Let's anchor this in real scientific standards. If the multiverse is real, convincing evidence would likely look like 1. A distinctive cosmological signature that fits bubble collision predictions better than any single universe alternative, across multiple datasets and analysis methods. 2. An inflation model that's strongly supported observationally and robustly implies eternal inflation under reasonable assumptions, which is subtle and model-dependent. 3. A deeper derivation of quantum probabilities that makes many worlds empirically equivalent but conceptually tighter, so the interpretation's extra baggage becomes extra clarity. 4. a predictive framework in high-energy theory where the landscape stops being a menu and starts being a calculator. Right now, we have serious theoretical frameworks, constraints and searches, ongoing foundational debate, not a smoking gun. Why do parallel universes hit us so hard? Because you are a creature made of what if. Every life contains the job you took, the love you missed, the risk you avoided, the version of you that could have happened. The multiverse, whether true or not, feels like the universe taking that inner human reality seriously. But science doesn't care what feels poetic. Science asks, what does the universe do when nobody's looking, and how would we know? So here's the clean conclusion. Many worlds is a legitimate interpretation of quantum mechanics rooted in Everett's 1957 work. Decoherence is a key part of how modern discussions explain the
Decoherence is a key part of how modern discussions explain the appearance of classical outcomes. Eternal inflation multiverse is a serious cosmological possibility, with ongoing work on potential observational signatures, including searches for bubble collision patterns in the CMB. String landscape discussions motivate multiverse-style thinking in some corners of theoretical physics, but the challenge is extracting sharp, testable predictions. None of these are confirmed facts. They are frontier hypotheses, some elegant, some controversial, all demanding humility. And if you're disappointed there isn't a final answer, good. That means you're thinking like a scientist. Because the most honest sentence in physics is still, we don't know yet, but here's how we might. If you want part 2, I'll do, can we ever test the multiverse? The 5 experimental strategies physicists actually debate. Drop part 2 in the comments and tell me which door fascinates you most. Quantum, cosmic, or strings? And remember, somewhere out there, in a different branch, you already commented. And it was hilarious.